we said last time that in this case for the transistor VDS is equal to VO, هيدا الدرين هيدا السورس هيدا الجيت and VGS is equal to VN. Okay. وجينا قلنا إنه if we want to find the solution at any given Vn, we have to solve for that IR is equal to IDS, and we know that IR is equal to VDD minus VO على R, and this is the voltage across the resistor, and IDS here depends on the region of operation. Okay. We started directly by drawing the voltage transfer characteristics of VO versus VN, but this time I'm going to draw graphically the load line and then continue where we finished last time. So أنا إذا في عندي ID للترانزستور versus VDS اللي هي VO للترانزستور, I know that the current characteristics for the transistor can be drawn as follows. Anytime that VGS is less than VT, the current هيكون بيساوي 0, and when VGS starts to be larger than VT, I would start to have higher and higher currents. So this is VGS3 greater than VGS2, and this is VGS1, and this is VGS2. هيك الكاركترستكس للكرنت بالترانزستور بيشتغلوا, and VGS is equal to Vn. هلا إذا بدنا نطلع على ريزستور IR versus VDS, نحن we know that IR is equal to VDD minus VDS على R. Okay, and therefore when what I need to determine the load line, so I need to determine two intersection points, one with the x-axis and one with the y-axis. Okay, so these 2 points are when VDS is equal to 0, IR is equal to VDD over R, and it is this point here. نحن شايفين هيك شي قبل. And when IR equal to 0, this means that VDS is going to be equal to VDD. فإذا هيدي هي point 1 إذا بدنا نسميها, وهيدي هي point 2, and between these 2 points the characteristics or the load line characteristics of the resistor exist. Okay, so graphically, if somebody is asking me what is the solution when Vn is less than Vt or VGS less than Vt, or what is the solution, okay, when if Vn equals to VGS1, okay, then I am operating at the intersection point of the load line and the IDS VDS characteristic curves, transistor current curves. Okay, this is what is happening. Now let us look at it, what is happening when the input is small and as the input increases, because this will clarify to us what we saw last time. When Vn, we have 3 cases. Okay, the first case is when Vn is less than Vt and of the transistor. This means that VGS is less than Vt. Okay, this means that the transistor is off, yani ID equals 0, and I am operating on these curves, ID equals 0. In this scenario, IR is going to be equal to 0. Okay, and in this scenario, what will we have? We will have VDS هتكون بتساوي VDD, okay, which is this point. So they intersect at this blue point here. Okay, so we call this point A. So the solution is at point A. لأنه IR equals 0 إذا بحط بالإيكويشن هون IR equals 0 بتعطيني VDS equal to VDD. هلا if we want to draw this on the transfer characteristics curve that we saw last time, we started last time with the transfer characteristic curves where we were drawing VO اللي هي VDS بهالحالة versus VN اللي هي كمان in this example VGS. We saw that VO is going to be equal to VDD until the input reaches VTN. يعني as long as the input is below VTN, my output is equal to VDD. So this is point A here, and this value is really VDD. Actually, I am operating at A for all values less than VTN. So the transistor was cut off. Okay. Now, the second scenario is when VGS increases slightly. So the second scenario is when VGS equals to VT plus epsilon. يعني ال overdrive voltage هو epsilon. So VGS is small. And since VGS increases this way, okay, so we can assume that I am operating maybe at point VGS1. Okay, and at point VGS1, I am I am operating mainly in the saturation region. ليش؟ لأنه ال VOV is small, okay, and VDS is greater than VGS minus VT than epsilon. يعني in this scenario, if I want to draw the curve properly for low VGS, okay, I would have saturated. My output is close still, my VDS is still high. بعد الأوتبوت شي عم ينزل لما أكون أنا على هيدي النقطة اللي هي VTN plus epsilon. We expect that the current will be small لأن ال overdrive is small and VGS is small, and therefore the output is still high. VDS بعدها قريبة من ال VDD. يعني VDS يلي هي VDD minus epsilon أو VDD minus مثلا إذا بدنا نحط epsilon is definitely greater than epsilon, and therefore the device is going to be in the saturation region. So حنكون نحن بال saturation region. Okay, and in this scenario we derived last time that V out is equal to, in this case, IR حتكون بتساوي ID اللي هي half K prime W by L ضرب VOV squared, and in this case we can find V out. So from IR equal to ID equal to VDD minus V out على R, we can find V out in as, okay, VDD minus RI, which is equal VDD minus half K prime W by L times R times VOV all squared. Okay, so هيدي region 2 continued. Okay, and then we said, well, the output as Vn is increasing, the current is going to increase and the output is going to decrease until I hit a point B اللي حنسميها هي ال edge of saturation ال EOS. And at edge of saturation, last time we said if my Vn is Vnb, my V out يلي هو VDS بده يكون بيساوي VGS minus VT يلي هو VIB minus VT. So I know that in this case my VO هو VIB minus VT, and I can plug this in the equation is A. Okay, so now we can plug it in equation A to say that VO is equal VDD minus half K prime W by L times R times VGS minus VT. And this is, we plug in for V out VIB minus VT. And we plug in here the value of VIB and we solve for VIB with one equation one unknown. So نحن صار فينا نطلع وين ال edge of saturation عم بيصير بهالcircuit. Okay. Now, as the input continues to increase, if I look at this equation or this circuit here, كل ما كبر الانبوت، كل ما الانبوت كبر مع ال VGS and a solution is moving to the right. So the maximum solution happens when أي أكبر input possible عندي إياه بالcircuit. What is the biggest input possible? شو أكبر input ممكن أعطيه للcircuit؟ فيني أطلع عن ال VDD. So we can assume that this is when Vn equals to VDD. This is the largest possible input. Okay, and in this case, the intersection point will be here. You can see that I am moving towards the linear region. Now, if we want to explain this without the graphical, region number 3 is beyond point B, اللي هي يعني beyond the edge of SAT. The device goes into linear region, particularly we are interested in solving for V out when Vn is VDD. يعني أنا بدي أعرف ال V out لما ال Vn بتساوي VDD شو بتساوي. So if we draw the transistor circuit again, we have now a large VGS here, which is equal to VDD at the Vn, and I am expecting a small output. لأنه عم يكبر الكرنت، الأوتبوت عم ينزل نزول كل ما عم شده through the transistor. The switch is closing firmly, and I am expecting a small output. So in this case, we can be sure that VDS is less than VGS minus VT because this is going to be a low output and VGS is equal to VDD. Therefore, بس نقطع ال edge of SAT نحن رح نروح على linear region, and حسب ما شفنا graphically, as we are heading, as VGS is increasing, the solution is moving to the right, and this is point C, and the output at point C is small. The output at point C is very small, therefore we can make sure that we are operating in the linear region. يعني هاي حتضل مكفية عم تنزل نزول, and when Vn is VDD at this point C here, the output is going to be very small. Okay, so we would like to solve for this output, and the way to solve for it is to set IR is equal to ID. Since it is in the linear region, the current is K prime W by L times VGS minus VT times VTS minus VDS squared over 2. Now, we can make some assumptions, okay, that VDS squared is approximately 0 because VDS is very small. In this case, it is the lowest possible it can reach. Okay, so we can rewrite the equation now in terms of IR equal ID, and we can set, and we know that IR is equal to VDD minus V out على R And if we look at the linear equation and plug V in here and plug VO here, we will find that this is equal to ID, which is equal to K prime W by L times VGS minus VT is VDD minus VT times VO. Okay, minus VO squared على 2 كنسلناها صارت 0. This gives me a solution that at point C, VOC is equal to V approximately لأنه كنسلنا square term VDD over 1 plus R times K prime W by L times VDD minus VT. Okay, so we now can solve for the lowest output VOC of the circuit, transistor resistor circuit. حدا عنده سؤال عن regions of operation or the load line graph؟ طيب okay. So great. So هلا صرنا we know that at point C we can find this solution. Okay. So this is point C. Okay. And we are going now to analyze a little bit this transfer characteristics of the VTC characteristics of this circuit. Okay, so this is VO, this is VN, and let us look at the curve. The curve has a negative slope. Okay, any input below VTN, the output is VDD. When the input is equal to VDD, the output بيساوي VOC يلي نحنا بنسميه VOL يلي هو low voltage level منه zero but it is low. So now I can think of this circuit and if I want to operate it as an inverter, okay, so I can have application number 1, which is to use this as an inverter. لأنه عندي الانفرتر عادة بيكون عنده input وبيكون عنده output, and the way the inverter works is if I input logic 0, it outputs logic 1, and if I input logic 1, it outputs logic 0. So let us look at this is I am inputting logic 1 and I am getting a logic 0. If my input is equal to VDD, okay, then I will get a low output. The output حيكون بيساوي VOL. And then also I can look at this circuit and see that if I input a 0, the output is going to be equal to VDD. So if my input is 0, okay, so when Vn is 0 or actually any number above VDD, below VTN, sorry, my output حيكون بيساوي VDD. So in this scenario, this is satisfying properly the properties of the inverter. So if I operate between these 2 points here, if I operate between this point and this point, يعني أنا إذا جيت بعتت signal اللي هي Vn as function of time, which operates between Vn as function of time, which operates between 0 and VDD, a square signal for digital operation. الأوتبوت اللي حيكون عنا هون هو in this form. The output is going to be the inverse of this value. Okay, and so on and so forth. Okay, So this is the output as function of time. فإذا this circuit is the basis for the inversion or for logic operation. Anybody has a question? Okay. طب so great. So أنا فيني operate بين الهاي واللو، أبعت signal بتغير بسرعة بين الهاي واللو، وبقدر أخلق inverter. And basically, if we want to write this down at small voltage, for small voltages, when Vn is less than Vt, Vo is VDD, and for large voltages, لما Vn close to VDD, then the output is very small. So we perform inversion this way. We can use this to build more logic gates. Okay, we can use this concept to build logic gates مثل ما حنشوف بآخر السيمستر، مثل النور NAND and other gates. Okay, طيب great. So هلا هيدا بيشتغل switch إذا بعتنا له signal. Let us now examine the intermediate region. إذا رجعنا طلعنا MOSFET as an amplifier. Application 2 يلي هي operating as an amplifier. Okay. إذا رجعنا رسمنا VO versus Vn. Okay, and we looked at the curve here. In the middle لعند الساتوريشن تقريبا لعند point B، يعني بين point A و B في عندي هون high gain region. Okay, so this is a high gain region, which means that if I operate at a bias point Q in the middle of the region, okay, in the middle of this region, if you remember in the beginning of the semester, if I apply an input signal Vn, if this is my Vn of t, then my output signal is going to be amplified. Okay, so my output signal is going to be Vo. Okay, so this will be my Vo of t. يعني أنا إذا ببعت signal as function of time, which is sorry, معنا اليوم قلبين الأكسس. This is time and this is Vn. So if Vn is centered at Viq and it is moving like this is inverting. So we will have a Vo as function of time, which is centered around some Voq. Okay, and it is inverted, and so, but it has a larger magnitude. Okay, so the output عنده VO peak to peak, والinput عنده VI peak to peak, and we will have a certain gain يعني هو VO peak to peak على VI peak to peak, or as we learned before, we can say that the gain is really the slope. So the small signal gain is dVo by dVn at point Q. Okay, so if I know Vo as function of Vn at this point, I can find the gain from this point. يعني أنا إذا جيت أول شيء حنعرفه إنه أنا إذا عندي هيدا السيركت هلا and I applied a signal Vn يلي هي Viq plus little Vi، حيطلع عندي الأوتبوت هون هو Voq plus little Vo. Okay, so I would be amplifying the small signal. So this is the small signal gain. Okay, هلا Q is in the saturation region لأنه الجين هو بال saturation region. And we already know from before that in the saturation region طلع معي equation لل VO إنها تساوي VDD minus half R times K times Vn minus Vt all square. Okay, so can I know what is the gain? بقدر أعرف dVO by dVn. I can use this equation for deriving or finding dVO by dVn. This means that dVO by dVn at Q is equal to minus R times K, صح? Yes, thank you, Wahid. Times Vn minus Vt, صح? I'm going to evaluate it at point Q. So this is going to be equal to minus R times K times VIQ minus Vt. هيدا هو gain less circuit. Sorry, but I need to fix. I think the broadcasting is froze. 1 second. Okay, so هيدا الgain. So we can find the gain because we have solved for VO على Vn in the saturation region. And what are the limits? شو هن limits لضلني بالsaturation لل Vn? What values Vn cannot exceed? ال Vn بده يكون قبل ال A، هيدي ال Vt يعني بيطفي الترانزستور، وبعد ال B بطلع من السات بفوت على linear region ببطل عندي amplification. Okay, so here I am bounded between Vtn and VIB. Okay, so the limits on the input to maintain proper, to avoid distortion. Okay, are points A and B. Okay, to keep it in set. لأنه هي الهاي gain region هونيك باللينير بصير flattening بضعف الكرنت. Okay, so the limits on the input, therefore we want VIQ plus Vin signal max تكون أصغر من VIB، وبدنا كمان VIQ، نشوف إذا بتساوي معناها، بدنا كمان VIQ minus Vin signal max تكون أكبر من VIA اللي هي VTN. اوكي، تكون أكبر من VT. اوكي، فإذا عندي two bounding points that I care for يلي I should maintain the input within and bias point Q within this region ليطلع عندي gain. Accordingly, if I apply an input VI plus VIQ هيطلع عندي output VOQ plus little VO, and this little VO هي حتكون A times يعني gain G، أحسن ما نضيع مع point A، هي حتكون gain times V. Okay, so this is what we will see in the operation of the amplifier. حدا عنده سؤال؟
دكتور بس الريجن اللي علمناها هي ريجن لشو؟
region اللي علمناها هي لما أنت بيكون بالsaturation region. بين point A و B.
VIP. اوكي.
اوكي، لأنه ال VIP هي ال edge offset وقبلها هون بيكون cut off، صح؟ وهون بيكون linear region، صح؟ so after B بنفوت على linear، نحن بدنا نكون بال saturation region. اوكي؟ thank you. طيب great. Good. So we will not always use those equations to derive or find the output. We are going to build it just like we built for the diode, a MOSFET small signal model اللي هو مهم كتير لأنه هيدا بس نلخصه you are going to use it in most of your problems. يعني نحن نعمل له derivation مثل ما عملنا للدايود the same way we did for the diode, and then we will use the model as is, knowing what the parameters are. Okay, and the model applies to both PMOS and NMOS devices, like two devices. Yeah, hello, we'll start with the derivation for the NMOS because the PMOS equations are the same. So I have a transistor where the input signal VGS, okay, is equal to VGS DC plus V little gs يلي هي small signal. نحن قلنا for amplification we are going to operate in saturation region. يعني نحن if we want to look what's the current of the transistor, the total current ID is going to be half K prime W by L times VGS total signal minus VT all squared. But the total signal VGS هيدي خليها K لتصير أهون هنا هي VGS DC minus plus VGS small signal minus VT all squared. Okay, so if we expand this quadratic term, we end up with ID, which is the total signal, تطلع عنا بتساوي half K ضرب VGS DC minus VT all squared plus K times V small signal VGS minus VT, okay, plus a quadratic term in the small signal in the sorry هذه هون بس ناقصة شغلة لأنه interacting sorry okay plus K ضرب VGS minus VT ضرب little VGS plus a quadratic component اللي هو half ضرب K ضرب VGS all squared. Okay, we are going to هيدي small signal وهيدي small signal وهيدي is DC. So this is ID DC, okay, plus some constant حنسميه GM ضرب VGS هيدي حنعملها ال ID small signal وهيدا الترم حنعتبر انه زيرو لانه VGS is a small signal هون وهي صغيرة فسكوير اللي لها صغير so we are going to ignore it. Okay, so فإذا the first thing in the expression of I big D حنقول we are going to ignore الترم half K times V small signal GS squared as long as it is less than assume that it is very small. Okay, and this really holds if VGS هي أصغر much smaller than 2 VOV. يعني إذا VGS should not exceed, and I'm dealing with a small signal, but it should not be larger than 5% of 2 VOV. So as long as my input signal compared to VOV, small signal compared to VOV is very small, I can ignore this term. Type great. Let us assume that this given is correct. Okay, so we are going to now continue from here, from this equation. So ID هتطلع بتساوي لكن half K times VOV squared هيدي هي ال ID DC plus ID small signal يلي هي K times VOV times VGS. Okay, so مثل ما درسنا بالdiode now, I can model the small signal current as some multiplier term times the small signal voltage. Okay, so بلشنا نلاقي إنه أنا إذا بدي أشوف شو هو small signal current ID إذا سميته بيساوي GM ضرب VGS هيدا بيعطيني إنه GM يلي أنا I'm searching for هي K times VOV وال VOV هي K ضرب ال VGS ال bias point minus VT. Great. So now I know my small signal current. هلا نحن we are going to memorize and remember this GM as this in this form. Okay. So هيدا الفورمولا اللي رح نتذكر اللي رح اكتبه هلا حنحط GM is equal to 2 IDDC على VOV. This is very important equation that you need to remember in this course. Okay, يعني هاي كتير مهمة equation.